Hello everyone, I'm Sharan. I lead the Samsung Neural team. I'm excited to be here to share with you the launch of Samsung Neural SDK. As you will see that this SDK is designed to help application developers seamlessly integrate machine learning into their mobile applications. The goal of this session is not only to introduce Samsung Neural SDK, but to invite your business models to come on board so that we can explore these opportunities together. To tell you more, I have two other speakers with me today. I shall start with the need for AI. What are the various ways in which application developers can deploy their machine learning models onto mobile devices? And with this context, I shall also talk about what is the value proposition that this SDK has to offer, and what are the various intelligence features that are powered by this SDK today. We are grateful to Derek, co-founder and CTO Polar Inc., who is here with us, who's going to talk about short suggestion feature, which we worked together for launch in Samsung Galaxy S10, which is also powered by Samsung Neural SDK. My colleague and architect Venkappa is going to talk about some of the internal details of this SDK, including the architecture, roadmap, and what is the workflow to get access to this SDK and so that you can integrate it in your applications. So before I get into Samsung Neural SDK, let me set some context. So the world that we live in today is continuously changing and is being revolutionized by AI. So as Gartner predicts, around 80% of mobile devices are going to be powered by on-device AI technologies by 2022. So we at Samsung believe that these are the four key components that are going to influence this journey. So we also call this as the ABCD of AI. So A here stands for algorithmic advancements. So as we progress, there are going to be significant advancements in algorithms. For example, if you want to do a depth estimation for every frame in a 4K video, this is a very complex problem. So the current algorithms have to evolve going forward, and that is what is going to define our journey forward. The second component is the big data. So there's a lot of data that is getting generated on mobile devices, and we are in a position to leverage this data to create some of the personalized use cases, suggestion engines, or recommendation engines. The third component is the compute. The compute power, as we know, is increasing year on year. For CPUs, for GPUs, and with the introduction of neural processing elements, this power is growing exponentially. So all of this together, when combined with domain expertise, we believe that developers will be able to create some of the next generation user experiences. So now that we know the need for AI, let's look at what are the various ways in which this can be deployed. The first way of deploying AI is cloud-based AI, where the machine learning models are hosted on the cloud. The request for prediction or getting an output is sent from a mobile device to the cloud. And the cloud does all the processing using the heavy compute power that is available, extreme, huge memories that are available on the servers. And the result is sent back to the mobile device. The second way of doing this is fully on a mobile device. This is where the models are deployed on a mobile device. Your inference happens on the mobile device. So the response here is real-time without any dependency on the network. There are some constraints associated with on-device execution of these neural models. These constraints include limited processing power, limited memory, and limited power and thermal budget. So Samsung Neural SDK is designed to bridge these constraints. We at Samsung also believe that it is always possible to leverage the best of both these worlds, about leveraging the cloud power as well as leveraging the on-device real-time experience of executing these models on a embedded device. So that's where we see hybrid is going to be the future for us. For example, if you're trying to do a complex scenario like food classification, so the basic level of categorization can be done on a mobile device to identify if it's a pasta or pizza or something else. Whereas a complex multi-model scenario to identify what kind of sauce is used, the geographical availability of this sauce, and so on and so forth can be offloaded to the server. So with on-device, the constraint that I talked about, let's look at why do we need to bridge these constraints? What are the benefits of bridging these constraints? So first and foremost, performance. Performance is going to define how the user is going to experience this application. So these DNN models are quite heavy, and there are the load time as well as the inference time is very critical for the application behavior. And that's where the loading of DNN model has to be optimized, the execution of DNN model has to be optimized. By the nature of these DNN models, they are going to bring in heavy load on the system, which means our CPUs, our GPUs are going to clock higher frequencies. And that's where power efficiency comes into picture, and we need to optimize these DNN models to be able to run them efficiently on mobile devices. Now, with growing camera resolutions year on year, we are seeing that the memory needed to load an image, to load a complex heavy DNN model, and to run the inferencing is going to be huge. That's where having an efficient memory algorithm to be able to use only that chunk which is needed at a given point of time is very important. Now, developers today are developing these applications not only for flagship devices, you also would want to deploy these on mid-tiers, low-end devices, and so on. So the challenge of bridging these constraints on other chips, on lower chipsets is even higher because of the capability of these devices are lower compared to the flagship devices. So what are the various domains in which these DNN models are getting built? So first and foremost, we believe that vision is at the forefront, where majority of DNN networks are getting built, new operations are coming up, and new use cases are getting built. Some of the examples in vision are object segmentation, object recognition, style transfer, and so on. So voice is another domain where we are seeing more advancements that are happening. Some of the examples include text to speech and speech to text, etc. So text is another domain where people are doing text classification and text prediction. Gaming is one domain which can leverage the reinforcement technology to be able to completely automate the experience for the user. AR is another domain where people are trying to create avatars, trying to track movements, trying to track gestures, and so on and so forth. So with Samsung Neural SDK, we've had experience to be able to deploy some of the models in the area of vision and AR. Voice and text is something which we are working on currently, and we hope to see that in the near future. And gaming is one area where we are trying to explore opportunities together with you guys. So if you have to build an AI application, what is the workflow that we have to go through? Let's look at that workflow. The first is you, as an application developer, would have to define a problem statement. You have to collect the data. You have to prepare the data, divide the data into training set, test set, validation set, define a DNN architecture, train this DNN architecture with this data. Once the network is ready to be with a desired accuracy, this process of training neural network is an iterative process where you'll be changing parameters, tuning the network, training it again and again. After you're done with preparing the model with the desired accuracy, you think of deploying it on a mobile device. And that's where your second phase of journey starts. And that's where you have to understand what are the capabilities of this mobile device. Is this particular machine learning framework supported on that device? Are these operations supported on that device? What are the compute units to leverage to get the desired performance? What is the memory available? There are so many things that you have to consider. And that's where Samsung Neural SDK comes into picture, and it makes your on-device journey effortless. So we started building this product 3 years back. And these are the 3 key goals that we had in our mind then, and which still continues to be these 3 goals continue to be most important goals even today. For example, the first one is about enabling execution of trained neural networks on device. So even today, we see a lot of developers are not able to run their models because either their ML framework is not, ML format is not supported on mobile device, or the operations are not supported. That's where we've started this journey to enable as many operations as possible, as many ML formats as possible. The second one is about getting the best performance out of these mobile devices. So developers are also seeing that the performance that they achieve on mobile devices is not up to the mark, is not up to what they get on a cloud or a server PCs. So that's where optimizing these neural networks becomes really important. Last one is about abstracting internal details from the application developer. We want application developers to be able to innovate and create new use cases. We want them to break out. We don't want them to worry about internal details of what is the hardware, what are the programming languages that I need to know to be able to deploy machine learning models. So now that we know what are the key goals, let's look at some of the benefits of this SDK. So first benefit is we want to cover as many machine learning formats as possible. So developers today are using cafes, TensorFlows, PyTorch, MXNet, Keras, and so many machine learning frameworks. So we started with Cafe and TensorFlow. The current version of SDK launched supports Cafe and TensorFlow. We're also looking at TensorFlow Lite and ONNX, which is coming up early next year. We believe that these four together can cover a wide range of ML frameworks. Today, we support a large set of pre-trained networks, which I'm sure my colleague Venkappa is going to cover in his session, including the operations that we support. We want to provide flexibility to application developers. Application developers, we want them to be able to choose which runtime to use, whether to use CPU runtime, GPU runtime, NPU runtime, or DSP runtime, with a desired precision on each of these runtimes. That's where the APIs have flexibility for application developers to be able to set this runtime, this precision, and so on. We also believe that a DNN model is a very valuable asset for application developers. And that's where we have introduced encryption method so that you can encrypt your models before deploying them on Samsung mobile phones. So now that we understand the value proposition, we understand the benefits, let's look at what are the features powered by Samsung Neural SDK with a short video. So these are the three features that you saw. There are 5 other features that are powered by Samsung Neural SDK in flagship phones, mid-tiers, and low-end devices. Scene optimizer, Bixby vision, short suggestion. There is selfie life focus for event segmentation, capture, image classification, and so on and so forth. So last year we also decided to work with some of the closed partners to realize some of the key solutions on flagship devices. Short suggestion is one such feature, and I hope we'll hear from the man himself, Derek. Yeah, please welcome Derek. Yeah, thank you.
Thank you, Sharan. Hi, everyone. Good afternoon. My name is Derek Yan. I'm co-founder as well as CTO for a company called Polar. We're a startup right out of Silicon Valley. My co-founder and I started the company 5 years ago out of Stanford campus, and the number one problem that I wanted to solve was how do we address the intersection of machine learning as well as photography. And we're very honored today to present shot suggestion, which was one of the key features that we developed last year in collaboration with Samsung, which is already available on the S10 as well as the Note 10 inside the camera app. So in terms of shot suggestion, when we first thought about this problem, it was actually a very complex issue that we're trying to solve, which is a composition problem. Typically, when we're playing with cameras today, you can tell whether a photographer is a good photographer or not based on 2 things. Number one is selection of lighting. The other one is composition. But when it comes to composition, this wasn't something that I could have done post-processing, where it has to be done directly when you're looking at that frame and figuring out what composition is the best one for this particular photo. And a lot of times it's very subjective. It changes over time. It depends on your personal taste, also based on trends. And this is something that's very, very difficult to address just using rules. And at the same time, we're looking at data when we're talking about training machine learning models. Biggest problem is where is that available data? And that's something that's also extremely difficult to gauge and collect at the same time. So what people come up with nowadays typically is using just very generic rules. So over here on the left-hand side, I have a picture of the rule of thirds, where you can see where the sky as well as the buildings are divided into threes, but those are very trivial examples, and they cannot be encapsulated for all of the use cases. So the approach that we wanted to employ was, how do we use a deep learning method to actually address this issue? And then the constraints, obviously, it has to be done directly on the device itself, because we're not going to have communication back and forth between the server and the camera, and at the same time, it needs to be low power, low memory. So the way that we tackled this problem was, okay, we can look at various crops that people are doing with a particular photo. And we can actually learn a lot based on how people are cropping photos that are imported and then how they're exported, just to look at which regions people find them interesting. And that was basically our data set that we used from our professional photographers in tackling this problem. The actual architecture of this model is very simple. This is not the model that we use, but it's very similar to a MobileNet V1 architecture, where we look at an entire photo, and then we come up with various crop candidates, and then come up with a scoring for each candidate. And then that's done through the last layer, where we have a dictionary with each candidate and each score. And to tell you what those scores mean, I'll go through a couple examples. So over here, we have an example of a photo, a very regular photo. And then when we look at how professional photographers are actually cropping this photo, and we analyze this data, we see a collection of positive regions and negative regions. Over here, the positive regions are red, where a photographer is most likely to crop out of this photo. And then the negative region are regions which a photographer would actually discard. And then what we see is the actual algorithm is able to learn what that particular region is based on this neural network of looking at various regions, assigning a score for them. Going to the next example, we have a person looking at the beautiful landscape in Europe, and then based on what the photographers are doing for this particular photo, we can see where the positive regions are as well as the negative region, and it's able to come up with the actual final candidate crop. And then the real-time operations, if you think about it, we have a camera feed that basically feeds in these frames at 60 frames per second, 30 frames per second. And then what we're doing is we're using this deep neural network to compute each particular frame and dividing them up into the candidate crops, and then looking at the scores for figuring out which one is actually best one. And then we determine what that target is, and we instruct the user to move to that particular target, and then constantly tell them to have this iterative process until they move to the actual target. And then all of that is happening directly on the device. But as we can see, the actual bottleneck is actually this crop engine, which is very, very difficult to fit onto a form factor inside a cell phone, just because we have to run hundreds of millions of computes before these crop regions are actually computed. So how do we address this issue? That's why we have these guys here. There is the neural network SDK that Samsung provides, and there are 4 main things that are awesome. So number one, there is a very simple script that you can convert an existing model from Caffe, TensorFlow, and I know these guys are supporting PyTorch, MXNet, and other frameworks. For us, it was Caffe when we first used it last year, and it was automatic, and it can be converted directly to a Snap model. And then at the same time, there's a lot of collaborations between our team and the Samsung team to figuring out what kind of layers, what kind of compute that's needed. So for us, I remember there was a ReLU 6 custom layer that we needed for this particular model, and they were very responsive, and we're able to get that directly. And the next thing, when it comes to all of these models, they're actually very, it's very data-driven as opposed to compute-driven. One of the things that we tried very early on was actually converting it into an OpenGL flow and then seeing what the performance is, but in fact, it was a lot slower. We tried it on TensorFlow Lite. So when it comes to actual doing all of these neural network operations, the cost of moving data is extremely expensive, and that's why we rely on the expertise, on-device expertise from the Samsung team to really leverage every single cent of that data movement as well as compute in order to achieve that speed up. And what we saw was a 10x speed up over TensorFlow Lite, which was platform agnostic. And then last thing was, in terms of the latest and greatest compute that are coming up. So this year we're going to have the NPUs, we're going to have the various DSPs as well as GPU compute. All of those things are directly leveraged through the Snap framework. So with that, I'm going to hand the mic back to Sharan. Thank you.
Thank you, Derek. That was an insightful session. Hope we have created enough understanding of this SDK and hope you guys are ready now for some of the internal details of this SDK. Please welcome my colleague and architect Venkappa Mala. Yeah.
Thank you, Sharan. Hello, everyone. Nice to see. I think at the end of SDC event, I hope you folks will enjoy.
Composition tips for your photo, like where to place the subject in the frame.
This is one of the things. Derek one actually. Okay. Hi. My name is Venkappa Mala. Here I've been asked to talk about Samsung Neural Core Framework. I believe that many of you are familiar with either one of Caffe or TensorFlow or Caffe2 PyTorch. Let's see how developer can use ML model into mobile app. We have two options. Option one, train a model from the scratch. Option two, use a pre-trained model with some customization. Option one is a more problem specific, and the hardware simply is not capable to train neural network from scratch in near future. Option two, it makes more sense to use a pre-trained deep learning model to do that. Perhaps this is a good option now. Let me start with neural converter. The neural converter, we have been introduced to convert DNN models between ML frameworks, which means you can train on one ML framework and deploy on another one. So like you take a model, Caffe model with a prototext, and TensorFlow PB model, and TF Lite model. And we have been introduced three key fundamental blocks. One, encryption, and second one, compression, and third one, quantization. Encryption, every mobile AI application developer would like to protect their model. We have recognized the need and introduced asymmetric multi-RSA algorithm and AES 128-bit. And second one, compression. Compression can lead to a reduction in the model size by 2 or 4 times. For example, TensorFlow Lite float inception v3 model size is 97 MB, around 95 to 97 MB. If you do FP16 compression, it's a half of like 47 MB. If you apply 8-bit compression, around 23 MB. Just imagine if our mobile apps contain several hundreds of models. We felt that it is an essential. That's the reason we have introduced the compression technique. But still, you can do inference with either precision, floating point or half precision. And third one, quantization. Current generation of hardwares like, recent generation of hardwares like DSP and NPU are only capable to support 8-bit fixed point. So that's the reason quantization becomes an essential. But the potential drawback of this technique is a slight degrade in accuracy, which is more or less important depending on the application. So, however, Samsung Neural, provide a guide based on the public model, what is the quantization error for networks like Inception V3, ResNet, and everything. So based on those networks, we can take it forward. All right. So with a neural converter, you can convert and model is ready. Next, move to your application. So application is ready to use neural API. So we introduce the neural API. It's a single click API to deploy a model in the production. It helps to abstract the underlying hardware accelerated devices. It also provides with a greater flexibility to select a preferred computing unit like CPU, GPU, DSP, and NPU. That is one of the key advantages of neural API. Choice yourself, depends on your need. That's how neural API helps. If you move to runtime, that is the third layer in application stack. We have designed with a lightweight graph representation to define a group of competitions to achieve adequate performance results. Because we understood that going layer by layer execution like cafe, it's a complexity. Complexity is involved to plug backends. That's the reason we introduced a graph. And also, if you look at runtime, left side, there is a ML parser. This is a runtime parser. Another key benefit of our neural architecture, you can run a open source public model without any neural conversion. But you may not get an optimal performance. Like missing of some of model optimizations, operator fusion, operator replacement, which are handled by Samsung Neural Converter. And second block, decryption and decompression we already discussed as part of Neural Converter. So we need to do inverse here. And the memory manager. So memory manager, we have introduced some of the state-of-the-art memory reuse buffer algorithms to handle. If you look at see, it requires a lot of memory. So if you don't apply your optimization techniques, it significantly takes a lot of memory. It hurts a lot. If I imagine that if hundreds of models, if concurrent executions are there, that's the reason memory manager is an essential. And the caching. Caching is a preloading. I think many people here are familiar with graphics, OpenGL they use, OpenCL. Imagine that if you do runtime compilations for the particular network and for those operations, we require more than hundreds of kernels. If you do it at runtime, it takes a lot of time. For example, in camera application, we do back and forth like front camera and rear camera. Within the front camera, again, we do the mode switches like beauty mode, live focus, and various mode switches. So end user looks for smooth transition. So that's the reason caching is an essential part. So that is one of the key advantage with Samsung neural architecture. And the last block of neural runtime is fallback. Fallback, the best part of this one is automatic fallback to the low order computing unit when higher order computing unit fail to support some of key operations or subgraph. For example, if NPU doesn't support like softmax or some detection output or some subgraph partition, in that case, seamlessly fall back to the lower order computing units. Could be the DSP, or could be the GPU, it could be the CPU. That is the beauty of this neural runtime. Let's move to the compute. This is our strength, because our journey started with the system software and heterogeneous computing, one of the core strengths. We have highly optimized heterogeneous computes for on-device AI inference. It means introduce a lot of state-of-the-art core algorithms like numerical optimization algorithms on embedded platforms for optimal decision making after n number of experiments on various chipsets. Here we have utilized advanced SIMD, hand-coded assembly kernels, optimal thread management. In fact, GPU delivers high performance after texture pipe utilization. Like that, we have done n number of experiments. That's how Samsung neural computes help a lot. Now, this is a brief of neural architecture. The precisions, typically CPU, GPU supports floating point and off precision. But if you look at DSP and NP supports only 8-bit as of now. Maybe near future we may see 16-bit fixed point. Let's move to the next slide. Some of the key operations noted here based on our experience. This is the just list. It's not complete list. You can find in Samsung Neural to get the complete operation list. Our intention is, your effort is a lot in the offline during training. To get the better performance on the device, some people want convolutions and deconvolutions like that. But if you want to use a neural, it's like AI processors like DSP or NPU, assume that if NPU doesn't support deconvolution, or even though supports, you will not get an optimal performance. In that case, what do? You look for alternative, right? So like Samsung Neural will help you to replace, like deconvolution in place of like bilinear and upsample. Some people do, like Derek showed in this diagram, 3x3 convolution, batch norm and ReLU, 1x1 convolution, batch norm and ReLU. The ReLU, but ReLU is a very good rectified linear unit. But the problem with ReLU is dying neurons. During training, disconnect the connections. People want to use ReLU and leaky ReLU kind of things to enable that with fixed slope, with a slight fixed slope, or for parameter slope. But assume that if again on-device hardware accelerators doesn't support those leaky ReLU or ReLU, in that case, what do you do? So again, Samsung Neural will help you to replace alternately without losing an accuracy. But of course, we may need to do some model calibrations. Together, we have to do it that. So however, Samsung Neural will provide a guide. You just look at the operation list and go ahead. We also listed some of the supported architectures. Because if you see, some of the architecture like SqueezeNet, MobileNet, 2 years ago we used MobileNet because we need a lightweight network. where CPU, GPUs we want to use, but slowly started DSP and NPU. So the complexities, people also started experimenting with complex networks like Inception v3 and ResNet. But decide that, for example, someone wants to do the classification or detection or segmentation. You can do mobile net with the SSD, object detection, or Inception v3 SSD or ResNet with SSD. People can do with all combination. But see the complexity. Mobile net and squeeze nets, computational capacity is 300 to 500 gigaflops. If you look at Inception v3, 6 gigaflops. And ResNet 101, it is more than 8 gigaflops. If you see the parameter and feature maps, like mobile net is around just 20 to 40 MB, whereas Inception v3 takes 100 MB. ResNet takes more than 150 MB. So what I suggest, decide how it helps for your application, which network is suitable. Choice is yourself again. But you should know the KPI, your memory and performance budget. Based on that, you select the appropriate network and start experimenting. If you look at the roadmap, first part we already discussed, correct now. In the second part, 2022 quarter 2 and quarter 4, we realized that aligning with the ecosystem is good, so that's the reason TF Lite started enabling. So we will see the next year TF Lite along with CPU, GPU 8-bit. And also custom operator. Here custom operator means we provide a workflow so that you can develop yourself, you can protect your IP at yourself. That's how it helps you that. And also, we keep supporting more operation based on the leading networks. And the fourth quarter, we look for standardization. Like many people, so when I interact with many developers in the outside, they prefer PyTorch. It's very easy to program. So that's how people want to convert PyTorch to on-device inference engine. In that case, standardization is important. So that's how we need to support ONNX so that MXNet or PyTorch Cafe 2, they can handle through ONNX on device. And also intermediate representation. See now, if you see, we have seen the backends like various computing units, CPU, GPU, DSP, and NPU. So seamlessly we need to plug in. And every week one operation is producing in the market. Every 1 month one network is producing. So that's how intermediate representation is one of the key factors which we feel that that's how we would like to enable intermediate representation. And also on-device training. So on-device training is like, as I mentioned initially, it's not from scratch. We do that accelerated on-device training on the device GPU. That's how it helps because we see the need and also industry moving to the more personalization. So people have started reinforcement learning, online learning, on-device learning, and various aspects. That's how we would like to position. And of course, we keep adding more operations. Before going to code walkthrough, I hope some of you might have gone through Code Lab. You might have experienced Samsung Neural, how Neural API can use in your applications. So pretty simple. It's hardly 8 APIs. We can directly use it in your app. If you look at create a model object, so these are obviously, you'll get the input name and output names, the model file and weight file. And look for the compute execution options. I have mentioned that you can select CPU, DSP, and also precisions. You can pass those here and create a session. With this, it establishes a communication between application with Samsung Neural. So what next? So now we prepare the model. Whatever I mentioned in that runtime is a graph. So we nicely prepare the required execution environment for the selected computing unit through open. Once preparation is done, just pass to the execution. In the execute call, this is the most critical. You get the required output and the selected output, and after that, you do post-processing. Then you can close your model using close and destroying snap session. Here, we do support concurrent execution through inserting multiple sessions. So you can execute, you can select and concurrently on CPU, GPU, DSP, and NPU. Now, let's move on to, let's recap with the scenario which a company, ABC, wants to build an AI application. Let's watch a nice video. Oh, sorry.
Artificial intelligence has paved the way for a new age in the mobile application space. And just like many other innovative startups, company ABC has been building AI capabilities for their latest mobile app. The neural network model powering the application has been trained on a cloud server-based system. However, running the model on the cloud is rather expensive, raises privacy concerns for user data, and introduces latency issues. So, company ABC decides to create an on-device solution, which opens up a new set of challenges, such as performance issues due to model size compression, compatibility issues due to MLOps limitation, and difficulty in choosing the suitable precision and compute unit. Ignoring any of these issues could potentially ruin the user experience of the app. Not something developers of company ABC would want, right? Thus, introducing Samsung Neural SDK, a solution that enables efficient execution of neural network-based applications on Samsung mobile devices. Now, developers can seamlessly deploy their app using the Samsung Neural SDK, which optimizes usage of the system resources and hardware components, making the application run smoothly with utmost efficiency. The Neural SDK supports most popular machine learning frameworks, a large number of pre-trained models, and a rich set of operations, enables network architecture scalability over all Samsung mobile devices, allows developers to choose from the available runtime, and ensures a robust protection of the NN models. Since the performance of the application is being taken care of, developers of company ABC can now completely focus on enhancing the user experience. Want to empower your mobile app with the Samsung Neural SDK? Visit the link below to apply.
I hope you have enjoyed the video. So, how to get Samsung Neural SDKs? Go to developer.samsung.com, apply partnership, and download it. And you can find the HTML page explaining the operator capabilities and computing capabilities and precision, everything, along with a sample reference, how to use it. And with that, you can deploy, you can start using Neural API to deploy AML model into mobile app. So you can partner with like Derek, you can demonstrate your application. So please reach out us, sdk.neural@samsung.com if any queries. So with this, I'm done. Let me invite my colleague Sharan for Q&A. Thank you so much.
Thank you, Venkappa. We're opening the deck for Q&A now. Before that, I would like to thank my team members who are here, the Samsung Neural team who have participated in the code lab and exhibition. And my boss, Raju Dixit, is also here. So any questions related to monetary things, I think he'll help me out in that. Yeah, please go ahead. You have to go to the mic and then shoot out your questions, please.
Still felt like a secret sauce of what you're doing. That's understandable. But what is the typical optimization you have seen when Snap is used and without Snap?
Yeah. So that's a very good question. So what we have seen based on our experience on, for example, Samsung Galaxy S10 is, without Samsung Neural, if you are using Caffe-based framework for deployment versus if you're using Caffe on CPUs or Snap with CPU mode, you would see somewhere about 2x to 4x performance improvement. If you're using GPUs with Snap on Samsung Galaxy S10, you'll see about 8x to 14x improvement. And that's where you saw Direct talking about 10x improvement with their solution. If you're using DSPs and NPUs, you'll see performance improvement in the range of 36x to 46x.
And it's with no drop in precision.
Yes. Yeah.
Do you see more devices coming with NPU support? What's the roadmap looks like for Snap on Samsung mobile devices?
So as of today, it's Samsung Galaxy S10 and Note 10 devices. There are versions which also support NPUs, especially the DSPs, which are out there in the market. We believe that there will be more devices, but we need to watch for that. Yeah.
Thank you.
Thank you. Any other questions? All right, then we'll close. Thank you.